for detection.
Sir?
Yes?
Why do you just have S1 hat and not S0 hat?
Good question. So I can't very well define this in terms of itself, so this is just a basis vector. This is a different basis vector. Later on I'm going to say this. And the specific meaning of the hat is that these vectors are normalized. But for now, that should do. So what's the meaning of this? So if we take S1, which is alpha S0 plus beta S1 hat, and we pass it through a filter matched to S0. And what are we really doing? We are doing this. Taking the sum from I equals 1 to NB of S1 of K. So now I'm using the vector notation. That should be equivalent to S1 of K times S0 of K. So remember, this is the optimal form of the matched filter. If I say H is equal to S0 NB minus K, really what that means is take up whatever thing is passed into the matched filter and multiply it by the elements of S0 in sequence. So that's really rearranging that convolution. This is what we get. So remember that from last class whenever you define H as H hat. So in the vector notation, really what I'm doing is I'm saying this. This is equal to S1 dot S0. But if S1 is alpha S0 plus beta S1 hat, dot S0, then what I end up with is alpha S0 dot S0 plus beta S1 hat dot S0. Okay, so this, let's look at this. What is S1 hat dot S0? Zero. So in fact, our matched filter wipes that guy out. And I just end up with alpha S0 squared. Or alpha S0 dot S0, which is alpha norm of S0 squared. Okay, so this is why when we talked earlier, we said there's not much point, or we assumed this. We assumed that S1 is equal to alpha S0, because if it's not, if there's some other component in a different direction, that component gets thrown out by the matched filter, like this. But what if instead we did this? Instead, we have two matched filters. Let's call this H1. Actually, let's call it H0 and H1. Where this is matched to S0, and this is matched to S1 hat. Then at the output, instead of a one-dimensional mean, I'm going to get a two-dimensional vector, like this, composed of the coefficient in the S0 direction and the coefficient in the S1 hat direction. So that's really where we're going with this. What I want is, and in fact if I do that, I should get, in the end, if there's any justice, this won't really work yet, but what I really want is that if S1 is equal to alpha S0 plus beta S1, what I want here is alpha beta, like that, where the output here would be alpha and the output here would be beta. That's the direction I'm going in. So in other words, although this is rejected by the first match filter, I set up a second match filter to capture this component. That's really what I'm doing. that's why I need this notion of vector space, because I want to determine the entire space in which my signals can exist. Okay, a couple more points for today. So that's the direction in which I'm going. To get there, I need a couple more tools. One is called an orthonormal basis. So an orthonormal basis, so remember, a vector space needs a basis. The basis is the set of vectors that basically describe everything that's in the vector space. An orthonormal basis is one in which with the following property. So let's say I have U and V are basis vectors, and they're our orthonormal basis. If, for one thing, the norm of U and the norm of V are both equal to 1, and U dot V is 0. So in other words, they're orthogonal, and they both have a unit length. So as an example of that, the Cartesian basis is orthonormal. So remember the Cartesian basis, that's x, which is 1, 0. Y, which is 0, 1. So firstly, let's show x dot y is 0. X dot y is 1 times 0 plus 0 times 1, which is 0, so that's okay. Norm of x is equal to 1 squared plus 0 squared square root, which is the square root of 1, which is 1. That's fine, and same thing for y. So in other words, the Cartesian basis is orthonormal. Now, if my basis vectors are orthonormal, that's when I start getting my two matched filters where each one outputs the component in that direction. So basically what I want is a signal space with orthonormal basis vectors. So one final bit of mathematical machinery that I need is orthonormalization. So it turns out if you have any pair of vectors, let's say A and B, and they are linearly independent, that is, there's no constant that exists so that A times a constant equals B. If that's true, then I can create an orthonormal basis out of A and B. The general form of this in n dimensions is called the Gram-Schmidt process, but in this course we only need 2 dimensions. So in that case it's actually quite simple. And we have a 3-step procedure. Firstly, we normalize A. To get A hat, A vector hat, which is A divided by the norm of A. And A vector hat is the first basis vector.